Hey, hello everyone. How are you doing tonight? So tonight we will have the preliminary design review for the 2021 Latin American Space Challenge Cooperation Program. We are developing a 5-kilometer rocket project. This rocket project has been is under development since July 2020. We have more than 100 people working this project. We have 28 teams from Brazil and other countries like India, Colombia, Peru, and Paraguay. And this is a dream for us because a 5-kilometer rocket is something that never happened in Brazil or in Latin America before, made by a student cooperation. So this is something unique. But before we go for a launch, we have to pass for every single part of a complex systems engineering. So the first step was the mission definition requirements that we did in mid-August. After that, we had in September the system design review, and tonight we will have the preliminary design review. So Calvin, we will stop to talk now, and I will pass the word for Vinicius that will present a little bit more of how this design review will work. But first, I want to thank you all for watching this preliminary design review, and also I want to congratulate every team member that is working here. So Vinicius, go on.
Hello, everyone. Good night. After all, thank you for being here, seeing our project. Of course, sorry. I am Vinicius Fernandez, the project director for the LASC Cooperation project for the 5-kilometer rocket. And tonight, for the PDR, what is the PDR? The Preliminary Design Review. The Preliminary Design Review is a third of a series of meetings for us to decide how the project is going to be. And what we are expecting for tonight. We are expecting the unveil of the project itself. We're going to see how the avionics is going to work, how the recovery is going to work, how structures and propulsion are going to work. All the teams presented here are going to present 4 subsystems, the 4 central subsystems of the rocket, of our mission. And each one of these subsystems represent as 3D models, schematics, simulations, and figures, engineering figures of what is what in each one of the subsystems. We are counting on them for the successful of this mission, and we hope that tonight we're gonna see what is the mission is gonna look like. The previous meeting was the SDR meeting. An SDR meeting is just so conceptual of the design, is how things gonna work. What we are expecting for each one of the subsystems is totally different from this night. This night is the unveil of the final draw of how things are gonna work. So for us to start, I will call the first presenter of the night, Sarah Hoddy and team for the recovery. Sarah, are you there?
Yes, I'm here. Good evening, everyone.
Okay, so I will ask you to present your work and best wishes.
Thank you very much. I'll be presenting now the work from recovery subsystem. So during this presentation, we are going to take a look at the ejection stage and the sectioning of the rocket and the descent stage. We're going to see about the parachutes and the cords and the expected performance during descent. And we're going to see some details about the deployment bag that we're going to use for the parachute and layout and assembly, how it's going to work, and some general subsystem information and estimations. So first, for the ejection stage, the shear pins have been dimensioned considering how much force they need to withstand during flight. And this is the admissible force that they would withstand for the shear pins placed in the nose cone and the shear pins placed in the propulsion coupler. So for the nose cone, we have 5 shear pins of 4 millimeters of diameter, and this gives us a safety factor of 1.73. Yes, 1.73, and demands a black powder charge of 6 grams to expel the nose cone. For the propulsion coupler, we will use 4 shear pins of 4 millimeters of diameter, and this gives us a safety factor of 2.22 and demands a black powder charge of 11 grams to section for the second sectioning of the rocket. So after the rocket, after the sectioning of the rocket, we will have some tension concentrations because of the inflation loads of the parachutes. And here, 2 scenarios have been analyzed. One of them is if the parachutes inflate before the cords stretch, which is the expected performance. And this gives us, well, the tensions as are pointed out. So 2.5 kilonewtons in the nose cone and 1 kilonewton here in the midsection. And here is the transition is very smooth, so it's negligible. And here is 4.3 kilonewtons. And we also consider a worst case scenario, which is if there is some problem during the deployment of the parachutes and the cords stretch before the parachute opens. So we're going to have a very high tension because we have 2 bodies separating in high velocity. And in that case, we have these tension concentrations in each one of the points. So we analyzed these 2 scenarios and obtained these tension concentrations to be able to design the structures to withstand these forces. And here, oh, I'm very sorry, this, no, okay, no, this is not in the wrong place, this is right. Also regarding the ejection, this title was wrong, I'm sorry. This is the ejection charges schematics, not the subsystem schematics, very sorry. For the ejection charges schematics, we have here 2 capsules for the black powder charges. One of them is a primary one and the other one is a redundancy. So this is where the black powder will be placed. And here we have this threaded pin that will go through the bulkhead and will be attached to the bulkhead with a screw nut on the other side. And here we have a little hole in this pin to pass the wiring for activation. And the other one is similar. It's a redundant capsule and redundant wire, redundant skip, so it's very similar. And during the descent stage, we have here the calculations for the parachutes. So the area and diameter, construction area, and the packing volume expected for both the main and drogue parachutes. And here we have the dimensions of the cords and suspension lines. So these cords were dimensioned to allow for the safe deployment of the parachutes and to avoid collision between the bodies, between these 3 bodies that will be descending in the 3 parts of the rocket. And this gave us, all these calculations gave us these final dimensions for the rockets and the suspension lines, which are the ones connecting the parachutes And also here is the diameter of the parachutes, just to give a better notion of all of these dimensions. And the expected performance during descent is a terminal velocity of 26 meters per second at 5,000 meters above ground level. So it's right when joke chute opens at apogee. At 500 meters above ground level, right before the main chute opens, it's expected to be at 19 meters per second. And the terminal velocity at ground level is expected to be at 10 meters per second. And this was designed to stand up to 50 kilograms of weight. And here you can see how the system behaves if we decrease the weight a little bit. So Structures is working on the mass optimization. And here you can see how the recovery subsystem would behave given this mass optimization. Now for the deployment bag. The deployment bag will be made out of thermal protective fabric, so probably Nomex. And the idea is to place these elastic bands here to be able to organize a little bit better the cords and suspension lines. So place these in both sides and organize the suspension lines on one side and the main cords on the other side. This mitigates the risk of cords entanglement during deployment, and also allows us to pack all of these things a bit more compact and occupy less space and demand less fuselage length from structures. So this is just a representation of what we are aiming for. And here inside be just the parachutes, and here the suspension lines and the main cords. And also here we have a swivel link to keep the cords from entanglement. It will be linking the main cords to the suspension lines. Now we have some general subsystem informations. This is a general schematics for the subsystem. So here this is the propulsion coupler, and here will be the lower part of the rocket. Here's the deployment bag. In this illustration, the deployment bag is closed. As you can see here, this little wing here is closed, and the deployment bag here is closed. So these are the main cords organized inside the elastic bands, the swivel link, the deployment bag with the parachutes and the suspension lines on the other side, the capsules, the charge capsules here, black powder charge capsules. And here the drogue deployment bag, very similar. The only difference is that we're going to add another swivel link here in the nose cone part, because the eye bolt placed in the nose cone is a screw nut eye bolt. So to avoid the parachute from losing up this eye bolt, we're going to place another swivel link at the connection to the nose cone. Here we have some weight, some mass and size estimations. So for this considers the parachutes, the cords, and the thermal protection. For the main chute, we expect it to weigh about 2.45 kilograms and demand a fuselage of 600 millimeters long. And for the joke chute, we expect it to weigh about 1.075 kilograms and demand a fuselage 300 millimeters length. These are the information that I have for today. Thank you very much.
Okay, thank you very much, Sarah. Okay, guys, now Sarah, you present everything. Is it done?
Yeah,
Yes.
so now we have a few considerations from the last part. Am I go to go? We are go to go. Jokes
Okay.
apart. So Tara, congratulations for your lead as a recovery leader. The project is amazing. Since the beginning, from the August to August 2020 to now, you and your team, you guys had a brilliant development of the recovery system. We can see, we saw now, we watched your presentation now. So you have a complete subsystem with every part that we wanted to put inside our rocket. So the drogue, the main parachute, we have a mid section where the avionics for the recovery system will be placed. So also you have all the data about it. For example, the parachute has a mass of 2.45 kilograms. The drogue chute 1 kilogram, average 1 kilogram. You have a 300 millimeters of section for the drogue, 600 millimeters for the main chute. So it's a complete analysis, and this is what we want for the preliminary design review, the direction for where we are going. So I just have two considerations, and after I will pass the word to Yamato, because he has a consideration that is very important. So my first consideration is that in the next meeting, that's going to be the CDR, the critical design review, I wish to see, to watch, and to hear about the rocket before the systems, okay? For the public, for the people not inside the Latin American Space Challenge Corporation, they are watching on the live stream. They don't know how is the rocket. The live stream start talking about the recovery system. So next time, please put the PMOs before the team leaders, okay? So this is not for you, Sarah, this is for the PMOs. About the presentation that you did right now, I think you are in the correct way. The preliminary CAD that you showed to us is very nice. I liked a lot, and I think you are in the correct direction. I just want to pass the word to Yamato, because he has a consideration about just a point, but we know that it's very important to talk about this right now. So Yamato, please go on.
Hello, Sarah. Hello, everyone. First of all, congratulations, Sarah. Great presentation. And I think from the first meeting we have, from now, we evolve a lot. So we have a very good and solid, we are going to have a really good and solid recovery system. My question and my comment is just about the speed of the drogue descent. I saw the presentation, it was around 19 meters per second for drogue, and the main will be opening around 500 meters, depending on flight simulation, of course. But I would like just to check this drogue descent speed. I think it's too slow for the drogue. First, we have the range area of our launch site. So we need to have a recovery range close to our launch pads. We have some restrictions, and if you have too windy or we have any kind of later deployment of drogue or main deploying first. We don't need that slow velocity of low speed of drogue descending. So my suggestion is to have the drogue speed a little bit, descent speed a little bit higher, around 40 to 50 meters per second. I think it's good enough. Of course, it depends on flight simulations that all the team are going to perform. But I think 19 is too slow, and all the system, including the drogue chute, will be very large. If you see the area of the drogue is and the sizing, I think it is too high, and the descent rate is too high as well. So my suggestion is to have slow descent ratio, higher descent ratio, around 40 to 50 meters per second, and this will allow a better recovery and as well a better volume and mass sizing of the drogue.
Okay, thanks a lot for these tips. I'm not sure that we're going to be able to achieve 40 to 50 meters per second, because there is this relation, this proportion between the drogue chute size and the main chute size to guarantee that they're going to descend at the same rate during the final descent. So, but I'm sure that we can make it higher. It's just probably not going to be as high as 40 to 50 meters per second, but I will pay attention to this and try to increase this descent rate.
Yes, just to understand better, you said that will not be possible because of the descent rate of the drogue and main. Would like to have both the similar descent rate. Why I didn't get it?
Because, well, since they're descending in a parallel manner, if their descent rate is too different, there might be a collision because of the bodies.
Okay, I think I understand. When you have the drogue open and the main open, they both will be inflated, and you want to then have to the same or almost similar descent speed. I think you don't have to worry about it. So when you have the main deploy, you will have a very large drag area, and basically the drogue will not affect that much. So you don't have to worry that much of being the two opening the same descent rate. They can have this difference, and the main chute will of course be larger and will generate a large amount of drag compared with the drogue one. So basically the drogue one will not be that effective of the out system. So that's why if you have a small drogue, the difference between when you have main and drogue, the drogue is basically you can ignore it. The main will let's say be the big difference here. So my suggestion is make the drogue smaller. Of course, you need it to your consideration and detailed analysis, but they don't need to be the same speed. Not sure if it was clear.
Okay, nah, it was clear. Thanks.
Okay, perfect. So we will have a little action plan for the drogue, making the drogue smaller for a high descent ratio of around 40 to 50 meters per second. For the main chute, I think we are go for the critical design review. So congratulations, Sarah, and our recovery team. So Vinicius, please go on for the next subsystems. Thank you, Sarah.
Okay, thank you very much, Calvin. Thank you, Sarah. Now let's go for the next part of the meeting. Now we're gonna see avionics. Avionics is a part about the electronics that is inside the rocket and give us data about how the flight is going, video data, video recording, and so on. So I'm gonna have presentation of Avionics from the João Fleury and team. João, can you hear us?
Sure, I can. I'm audible.
Okay, you are allowed to go. Best wishes.
Okay, thank you, Vinicius. I'm visible.
Yes, João is going to put the slide on the screen for the live stream part, okay? Just a second. So, go on.
Okay, thank you, Calvin. Thank you, Vinicius. Thank you all that watching us. Now I will present the Avionics subsystem that our system will be responsible for trigger the recovery to capture flight data, capture a video of the flight from the ground to the apogee, and also we will send data to allow the recovery of the rocket. I will start presenting where the avionics will be placed on the rocket. So to ground to the top, we have the engine in the beginning. After that, we have the recovery, the gunpowder charge, and the midsection. And the midsection, you have the payload bay, and after the payload bay, you have the main board section and the midsection that is our system. And above us, we have the other gunpowder charge to trigger the drogue recovery, and after that the cone. To trigger we are responsible for trigger the both recovery, and to do that we will have wires from our bay to the bottom and the upper part of the rocket to trigger the gunpowder charge. Here we have the design of how the rocket, and here in transparent material are the midsection, and here the avionics bay. Now, in this picture, we can have the avionics bay with more details. And in the upper plate, we have I'm sorry for that. The upper part, we have the video recording section that are responsible for recover and broadcast a live video from the rocket. And in the middle of the avionics bay, we have the main board section with all the sensors and the transmitter modules, and the recovery trigger below the main board. And below everything, we'll have our batteries to power our system and to allow it to complete the missions. Here we have a CAD of the rocket. So as I say, we have the engine, and after that the recovery, the midsection with the payload bay here, and our system here. And in more detail, our avionics. So in the upper plate, you have the cameras with his DVRs and transmitters, the main board with the barometers, the GPS module, the connectors to connect the wires to recover trigger, and below everything, we have the batteries. Now I will pass the word for Olavo to present in more detail the VR section.
Hi, John. I'm here. Good evening, everyone. This is Roberto. On this slide, we can see the main elements of the video record section, and I will describe each one. At the right top, we can see the FPV camera responsible for capturing the images and in HD quality. Below it, we can see the DVR device that is responsible for recording the captured images and convert them to analog format. At bottom left, we have the omnidirectional antenna responsible to connect the receiver at the ground station. Above it, we have a camera cover responsible for mechanical and thermal protection of the camera. And finally, at the upper left corner, we have the FPV transmitter which will operate at 5.8 gigahertz, sending all the images to the receiver on the ground station. Now, I would invite Olavo to speak.
Good night, everyone. I'm Olavo. So here we have a schematic of our subsystem. In the top part, we can see the VR bay, the system that will be embedded on the rocket. So our first element is our camera. There will be 3 sets of cameras, DVRs, transmitters, and antennas. So we can take a 360-degree view of the rocket. And the camera will be connected to this VR, so we can convert the signal from digital to analog, and also save the video in an SD card. There will be also the transmitter, who will take the video from this board and use the antenna to the ground station. In the ground station, we have 2 antennas, one directional and one directional, and a video receiver that will be responsible for receiving the video, and connecting this receiver to a video capture board, and connecting the capture board to a computer. We are able to live our flight to the world on YouTube. So, John, can you pass the slide, please? For the fixation of the camera, together with the structures and aerodynamics team, we designed this standard, and the camera is put on a 30 degrees angle from the rocket structure, because our camera has a 120 degrees angle of view. So with that, we are able to see the ground and the horizon line during all the flight. This is all I had to say. Thank you for listening.
Good evening. Now let's talk about the main board sensors and how the sensors are distributed on the board. In the image, we have a 3D representation of how the sensors will look on the plate. On the first floor, we have in the first floor, we have the PION altimeter, and in the second floor, we have all the components chosen for the main board. Something important to say, it's about the distribution of the components. This is importance depends of the functions. For example, the radio LoRa module in the corner because of the antenna, and the connections for recovery trigger also in the corner because they go outside the plate. Can you change the slide, please? Here you have the main board design. This is the PCB view. PCB means printed circuit board. In the first image, we have the 2D representation with the top view. Here we have the sensors and the microprocessor. And we also can see the tracks. Tracks are used for the electrical connections of the circuits. And in the second image, we have the representation of the PCB in 3D. And have the same idea for that's the first image, but now we can see better the components. Now Rogério will speak.
Hello everyone, my name is Rogério. I'm here with the team in the avionics session. We're going to talk about the recovery trigger system. So in this schematic, we can see in the left the main one, and in the right the redundant one. The main one we designed to be in the main board. So the ESP32 will take care of that. So, and we have sort of like switches, the mechanical switches, but it's just to exemplificate the removed before flights. We're going to talk after in this presentation. It's a safety measure that we can take to not go without the charge with the battery. So when the rocket achieves the apogee, that is the higher altitude, the ESP32 will send a signal and will activate the recovery trigger system. And the redundant one is the PION altimeter. The PION altimeter, we have to take care. We have to take some precautions that they won't trigger at the same time. So the PION altimeter will have a delay after the apogee is achieved. It will trigger some moments after. So even if the main one fails, we have the PION altimeters to ensure that we will trigger the recovery system. You can go to the next slide, please. Next slide, please, João. João?
Guys, we had a little break. João just lost his connection. I'm sending him the link again.
Okay.
Just a little time. You can continue the presentation.
Okay. The next slide is how we're going to trigger the system. We had the idea with MOSFET and skips. In the earlier presentation of recovery, they showed us that there are skips and inside the recovery bay. So the skip is basically a wire. When current goes through it, it hits, and there's a small portion of black powder in it, and it creates a sparkle that can ignite the black powder inside the recovery. The MOSFET is a transistor, is a field effect transistor. Almost, it's a different transistor from the BJTs. The BJTs are current boosters. The MOSFETs are voltage enhancers, voltage amplifiers. So it works when you apply a signal, a voltage in the gate. There's the gate, the drain, and the source. When you apply voltage in the gate bigger than the threshold, it works like a closed switch between drain and source. So when applied, you can close the switch between drain and source, and current can go through, and so can apply voltage between drain and source. Next slide, please. And here's the schematic that we thought to the recovery trigger. We need two, because there is the main chute and the drogue chute. So both of them will have the main trigger system and the redundant trigger system. So we can see that in the drain, there is the VCC, there is going to be the battery, the voltage source. In the gate, there is the signal that will come from the ESP32, or if we're talking about the redundant trigger system, will come from the PION altimeters. So the gate is from the signal, the drain will be the voltage supply, and the source will be the skip that goes to ground, that is 0 volts from the whole PCB. If you can see, there's this resistor between gate and source, is to prevent voltage variations that can trigger without the unwanted trigger of the recovery system. So it's for precautions, for safety. And another image is from the connectors. We have the skip drogue and the skip main connected to the ground. That is where we will connect the skips, and we'll go to the recovery system. And now I'll go pass, you can pass the slide, and Lucas will present.
So as Rogério said, we have a redundant trigger system that is explained by this schematic on screen. Basically, we have a separate battery and a separate everything from the main trigger. So if anything fails the main trigger, we have a separate one working on the redundant one. So we are basically sure that it will trigger when the time comes. We can pass to the next slide. you can go to the next slide.
Oh, I'm sorry. I'm having some problems with connection. In my screen, I already changed it.
Okay, it's changed now.
Oh, nice.
Thanks. So the remove before flight system works with a component called switch snap action. It works like a button that activates or deactivates a relay. So when a rod presses the button on the switch snap action, we open the gate to the battery from the mainboard, so it won't get any power. But when we are ready to launch the rockets, we remove the rod and the button is released, closing the gate, and then the mainboard has power and everything. This is useful because we don't waste battery when we don't need to, as well as keeping the components safe from any problems from it being turned on too long. On the next slide, we can see some schematics of how this will work and how the switch snap action works inside. Basically, it's just a relay where you can connect or disconnect some metals to let the current through. And yeah, it will be separating the battery from the main board when we don't want to. Now we have Rodrigo with the next part.
Good night, everyone. I will talk a bit about the operation that we'll do in the day of the launch. About the video, the first thing, when we are ready to go, we will take off the remove before flight key, and then the system will start to capture the video and transmit the data to the ground station. And it will continue like this until during the whole flight and during the recovery. And we will only turn off when if the battery ends, or if we recover it before the battery ends. You can pass the slide. Okay, about the main board, it's a little bit more complicated, but it's simple. The first thing, during the integration part, we will turn the system on, and the system will automatically check the sensors, which means it will read the sensor and check if it's a plausible data. It will create an SD file and write and read data to it to check if it's okay. The GPS will be sending data if it's working properly. It will be sending data by the LoRa. And yes, we can check LoRa if checking if we are receiving data. Okay, then it's during the integration part. On the launch pad, when we are ready to go, until then, the system will be at a low consumption mode to save battery. But when we are ready to go, we will remove the remove for flight key, and then it will be on, which means the system will be transmitting altitude, deceleration, and other data flight, and it will be checking liftoff. And for this, from this point on, it's full autonomous. Okay, after flight, the system continues on, but it's not checking like for apogee or things like that. It will be only sending GPS position to help the recovery. And when we find the rocket, we will shut it down. Okay, you can pass. Thanks. And finally, there are some conditions on the avionics part that we have to abort the launch. It means that it is a way that we have a safe launch. Some conditions are something like if the SP32 fails, which is our microcontroller, we can't launch without this. We have two barometers in the rocket. If both of them fails, we can't launch also, because it is our main way of detecting liftoff, apogee, the altitude of deploying the main chute. The GPS, we can't launch without the GPS, because that would complicate a lot the recovery. The micro SD, we can't launch without it, because even though we have another way to save data, the micro SD is our main way, because we can save a lot of data. so we can't launch without it. And the lower also, because that's the way we receive the GPS position. So without it, we wouldn't be able to recover, or it would be really harder. And now I will pass the words to João. He will conclude the presentation. Thanks.
Okay, thank you, Rodrigo. Thank you all that present. That was our avionics system, that the job that we developed during the PDR phase. And now we were open for questions. Thank you all.
Okay, thank you very much, João. Now it's open for questions and answers with Calvin and Tim.
So yeah, I'm here. Yeah, let me just unmute. Yeah. Welcome everyone. Again, and I'm just gonna congratulate you guys on the amazing job you did. It's really a great system. It was really well made. We really liked every image you showed us, and we really liked that you had a lot of images to show. So we had a lot of we saw the rocket maybe for the first time, I think. So that's something really great. And the CAD design of the little recovery session and the Avionics bay, it's very good. So yeah, that was really great. And for the considerations, I think that on just a small question, on the CAD you had a normal omnidirectional antenna, but later you referred as a clover antenna, right hand polarized, I think. So you are going with the clover antenna, right?
About the antennas, on the rocket we'll use omnidirectional antennas. And for low rate on the ground station as well, we make some link budget simulations, and we believe that the omnidirectional antennas can handle the data transmission with no problem. But regarding the video, we will assemble omnidirectional antennas on the rocket, but on the ground station, as you can see in that slide, in that image,
yes,
we will have a directional antenna on the ground station, and it will track the rocket during the flight.
Okay, that's really great. This slide that you're showing right here is really resumes everything of the VR subsystem, and I think that you really did a great job here. There is a lot of information about where something is going to be plugged and everything else. And just the other consideration I have, here on this system, you are basically using the remove for flight on the batteries, right? So you can unplug the battery from, when you unplug the remove for flight system, the system will start to work, will be powered up. The antenna part you already covered. So the other thing is, it will be better for the recovery part of the system to be like this, with the remove for flight part on the battery. If you could pass like 3 or 4 slides front to show the recovery part, because yeah, on the right here on the presentation, you are putting the remove for flight between the canister and the system, and some people have some concerns about some people on the rocketry forums on the web, some experienced people, they always say you have to cut the battery instead of the connection. It's safer to cut the battery with the remove for flight. So in this case, we could like remove these 4 remove for flight switch that you guys are showing here, and just insert one on the battery, like on the PION altimeter light, because when you kill the battery of the system or the main connection there, it's safer because there's no system being powered up. When you are, for example, I think the plan is to assemble the rocket on the rocket assembly area and then carry the rocket to the launch pad. And in this process, having a system already powered up and with, for example, a remove for flight that can fall or something like that, the system will become active or some other thing. So maybe adding 2 remove for flights, 1 for battery and 1 for example, enabling the pyrotechnic charges or something like that. You can use, for example, just because of this, we can turn on the rocket, for example, when we insert the rocket in the launch array or in the launch base or launch pad. And you can like exchange these 4 switches to 1 on the battery for the main board, and if you want another one, you can use like a normal digital pin on your microcontroller to put another one that will be read as high or low, just for controlling if you can or can't enable the systems. It will be easier for you, and it means the same thing as these ones. One could like criticize saying like, oh, but in this way you are disconnecting the pyrotechnical charge, and you are right, you are really disconnecting, but the system behind it is energized and could do some damage as well while carrying the rocket from places from place to another. And I think it's better if you do something in the battery as well. But you guys weren't wrong. It's just that is more commonly used in the rocketry to cut the battery, really unplug the battery from the system. That's the behavior of all the recovery boards, like the PION altimeter light, the stratologger, and the other altimeters out there. They really cut the connection between the battery and the other parts of the system. So the system is only powered up when it's on vertical position or something like that. And that's it. The other parts are really great. And the main board and the battery there, you did a really great job. And yeah, that's really it.
Okay, thank you, João Pedro, for your advice, for your comments.
Nice, thank you, João. Thank you, João, for your presentation, for all the team responsible for the recovery system. I just want to show, I think you guys are working with the PION altimeter, and you guys you need to see that. Okay, let me see. Okay, we have the PION altimeters here. So probably the first time you guys are seeing, we have a lot of altimeters here. So in the next you guys will receive this for the project. Okay, so thank you so much for the presentation. I really liked all the systems, and also I'm very anxious to watch the rocket going through the 5-kilometer apogee with a live stream from the onboard camera. So thank you so much. That's it. Guys, do you have any more words?
No comment, that's from my side.
Okay, Vini, the word is yours. Let's go to the next system. Congratulations with Avionics. You guys are go for the critical design review in 2021. One step closer.
Okay,
thank you very much, Calvin.
Thank you all.
Thank you very much, João. Thank you very much, João, and the team. This was a very nice and complete job, as you saw. A lot of edge engineering going into that. Now the next part is structures and aerodynamics with the PMO Augusto and the team. The structures is, of course, one of the most important parts of the rocket because it keeps everything together. So a lot of engineering goes in these subsystems, also ingenuity to solve all the problems about weight reduction, stability of the flight, payload, and of course, keeping everything together and well assembled. Now, Augusto, can you hear me?
Yes, I can. Hello, guys. Hello, everyone.
Hello, everyone. It's
I'll
with you,
share
Augusto.
Okay, I'll share my screen now. Okay, are you guys seeing the presentation? Okay, so let's start. So we'll start with the best part. We'll start with our rocket. So this is the first complete CAD model for the 2021 LASC Cooperation Program. It is honestly a really beautiful rocket. We are really delighted to show you guys this picture. Now talking about some general dimensions of the rocket, it is 4 meters and 8 centimeters high, so really high, and has 17 centimeters of external diameter. The whole rocket can be divided in modules that, if needed, may be manufactured and integrated in different locations. Okay, so to be a little bit more specific, we have 5 modules. The first one is the nose cone, then the nose section, then we have the mid section. Actually, I said the nose section, right? It's the drogue section, then the mid section, in which we'll be placing the avionics and the payload. Then comes the main chute section, and finally the motor section. Okay, now we're going to talk a little bit more about the aerodynamics part of our subsystem. And to tell you guys a little bit more about this, I'm going to call Rafael. So Rafael is with you.
Good night, everyone. I'm Rafael. I'm part of the aerodynamics team for the cooperation program. And let's start our analysis with the expected flight profile for this rocket. So this is a table with the main events of the flight. We start with the launch rod exit at about 0.44 seconds into flight, followed by subsonic flight. The subsonic flight will last for about 23 seconds, including the acceleration and deceleration periods. The transonic regime will last for about 9 seconds, and Mach 1 will be achieved during this period. The maximum velocity will be Mach 1.13 at about 3.7 seconds into flight, and apogee is expected at 32.1 seconds into flight. Next slide, please. So for the optimization of the aerodynamic components, we used genetic algorithms, which is a simple way to optimize designs without having a heavy computational cost. The cost functions of this algorithm take into account drag, weight, and stability. The algorithm changes the dimensions of the components, excluding the configurations that are unstable, and it tries to minimize the drag and weight of the components. The results of this optimization will be shown next. Now, with the nose cone team.
Good night, everyone. About the CFD simulations we made, the objective of them was to verify the most optimized geometry that would generate the lowest drag coefficient for the cone and the boat tail, because doing the calculations for each case would be very complex. So with the help of the software, more accurate values could be obtained. So basically, we defined several geometries configurations for both, and thus to be calculated at different max speeds. These configurations were implemented to simulate the flight of the rocket. Starting with the cone simulation, the nose simulation, several aspect ratios were generated to verify the influence of the elongations in the drag coefficient. From the result, we can see that during the subsonic flight, the frictional and pressure drag are very influential. From the transonic flight of Mach 0.9, there are parts of the cone that are speeding above Mach 1, thereby generating drag due to the wave shocks. Thus, from the transonic to supersonic flight, the wave drag is more influential than the others, concluding that larger aspect ratio is more advantageous. So, the cone simulations generate a lot of data for the optimization scope. The L over D configurations equal 4 ended up being chosen due to the small variations in the drag coefficient during the flight, beside of the other factors. Here we have the full flight variations of the CD for different aspect ratios, and the appearance of shock waves in the high velocity in the right image. Next slide, please. Here is the detailed behavior of the CD for the subsonic, transonic, and supersonic flight, as I had explained before. Now we're gonna explain the boat tail.
Just like we did for the nose cone, the boat tail simulations were made by varying the length and the angle through different Mach speeds. In the results, it was possible to see a very strict pattern for subsonic and supersonic speeds, in which the CD would tend to decrease with the increase of the angles for subsonic regime and increase with the angle for the supersonic regime. But for the transonic regime, it was possible to see, as it's possible to see in the graph in this slide, they didn't follow a steady pattern. They actually started decreasing with the increase of the angles, and then after around 12.5 degrees, they started to have an increased tendency with not such a clear pattern. Next slide. Now we're talking about the fins.
So all the aerodynamic components, that is the fins, the nose cone, and the boat tail, were optimized after running the genetic algorithm made by the team. For the fins, the following dimensions were selected by the optimization script, as you can see in this slide. Additionally, the algorithm determined that the use of 3 fins were more efficient than the use of 4 fins. Next slide. To increase the structural strength of the fins, the material selected for its manufacture is the carbon fiber sandwich with balsa wood, and the total maximum thickness of the component was set as 5 millimeters. As for the stability, the set of 3 optimized fins provides a static margin of 1.7 in the moment that the vehicle leaves the launch rail. Next slide. This is the preliminary design of the fin profile. The hexagonal profile was chosen to decrease the shock wave formation, avoiding stability loss and decreasing the wave drag. The dimensions were chosen to viabilize the manufacturing process, avoiding small angles and dimensions, and at the same time, to provide a high aerodynamic efficiency. Next slide.
Good evening, my name is Bruno and I will talk about the nose cone structure. The nose cone will be divided into 3 parts: tip, composite body, and internal threaded bar. The tip will be composed of 2024 aluminum, which has great strength to withstand the transonic and supersonic regimes. It will be connected to the rocketed body through the threaded bar that will use the eyelet and the upper coupler to be threaded. And finally, the composite body will be made of VU 130 fiberglass due to its low cost, its great capacity to withstand the stress to it will be subjected. Next slide, please. Now, talking about the dimensions of the nose cone, we have 170 millimeters in diameter and 680 millimeters in length in its general structure. 60 millimeters in diameter and 140 millimeters for the tip. And finally, we have the threaded bar with 590 millimeters. Next slide, please.
After completing the drag coefficient simulations for the boat tail for different lengths and angles, and applying the values into our optimization code, we obtained the optimized geometry for the boat tail of a truncated cone with a length of 0.5 calibers and an angle of 11.9 degrees. After some thermal analysis and as means of waste saving, it was decided that the boat tail should be made of PLA filament by 3D printing because of its cost-benefit ratio. Besides all of that, it was determined that the boat tail would be fixed to the rocket by the motor screws through some attachment points made on the boat tail attachment zone, which is the thinner part right there at the bottom in this image. Even though the thermal analysis of the nozzle did not get ready, it was made a research of the different possible thermal insulators which could be used in case of the temperature around the nozzle gets higher than what the filament can resist without deforming. Next slide. Here we've got some images of how the optimized boat tail should behave under supersonic regimes. The first image shows how the airspeed around the component should react under supersonic or transonic speeds. And the second is about the pressure around it. It's possible to see that the pressure drag should be like very not so high as other boat tails would be, and so this explains why this boat tail was chosen and how efficient the optimization code is. Next slide.
Okay, so now we're going to go to the second part of our presentation, which is more related to the structures part of our subsystem. So first of all, the first thing that we did on the PDR was to make these basic force diagrams that you're seeing now. This first one is the actual force diagram. It considered the effect of the aerodynamic actual force, which is kind of the drag, but not quite the drag, but you can understand it as being the drag. The weight of the structure, the inertial force created by the acceleration, and the thrust produced by the motor. A number of critical scenarios were considered, resulting on the following maximum values for each section. So you guys have here the critical force that we found regarding the actual force. Okay. Then we analyze the normal forces acting over the rocket, which are the normal aerodynamic force and the decomposed weight in some cases. In our case, we consider a scenario in which the rocket will be submitted to a velocity of 400 meters per second, will have an angle of attack of 5 degrees, and a decomposed weight considering a launch angle of 5 degrees as well. That resulted on the following results. So these are the maximum normal forces acting over each section of the rocket. Then finally, we only got that LASC graph, and we just integrated it to obtain this graph here. That is the bending moment graph. And the results are the following: the maximum moment applied to each section of the rocket. Okay, so with this data, we were able to perform a number of tension analysis, and after that, we were able to settle the dimensions and the materials. Another important loads that will be applied to the structure of the rocket are the inflation loads, the pressure vessel loads, and we'll also did some thermal analysis. Now, Lucas Sauer will tell us a little bit more about the coupling system.
Good evening, guys. Talking now about the coupling system. From the STR to the PDR, many changes have happened. Some of them are regarding the internal structure of the rocket, and others of them like with the propulsion. To quote, we can say about the bulkhead of the motor that will not be the same way as it was supposed to be as in the SDR. Now it is attached both to the coupler and the fuselage. The male-female system was kept in order to ease the assemble and the integration of the rocket, and with the design defined, we started the analytical calculations considering the forces and loads that Augusto has just told us about, and the yield strength limit of the material that we chose, and also the areas that we've got. The material defined was then the aluminum alloy 6351T6, that is a material with similar properties as aluminum alloy 6061T6, that is a largely used material for rocket industry. With that enhanced the material and the dimensions, we could set the mass with software helpness, and it was like 1400 grams with the software helpness, as I said, which was inside the expected for the couplers. Simulations are about to be done, finite element analysis that will have to match with the analytical calculations to see the internal efforts. Two important points of the definition of this design is that the material was defined considering that the zippering may occur with other material. The zippering that may occur is coming from the recovery, And the other point is that there will be no more screws attaching the fuselage to the coupler. There will be epoxy adhesive. This decision was taken in order not to make holes on the fuselage and preserve its integrity and its stability. Can you pass, please, Augusto? So here we can take a quick look at the dimensions that the coupler has got. You can pass now. Talking about the upper coupler now, the system is very similar to the main coupler. Its total height is like 45 centimeters. It must have the parachutes in its space. It also has some shear pins for the recovery. It has a place for putting an eyelet that hold the parachute. And optimizations were done with it, considering its attachment with the nose cone. You can pass now, Augusto. Talking about the mid-section drug coupler, it will connect the mid-section to the rocket to the drug section. It was designed to sustain an inflation load of 4,000 newtons, and like the others that we have presented, it will be made out of aluminum 6351T6. It has holes for the threaded rods of the middle section, which will be presented soon. The recovery is eye-bolt and powder capsules to be attached to it. To make the assembly easier and more versatile, it was decided to use M6 screws to attach it to the fuselage. You can pass now, Augusto. Additionally, we have also the coupler that will connect the middle section to the main chute section. It has basically the same design as the previous one. However, due to the higher predicted inflation loads and pressure loads, it's thicker than the last one, and we will also use M8 screws to be attached to the main chute body too. Now Rodrigo will be talking about the motor section of the rocket. You can go on, Rodrigo.
Thank you. Good evening, everybody. Continuing the efforts made in the SDR, in the motor section, all the dimensions have been set for each subcomponent here in this phase. For the fuselage, we decided to work with the following dimensions, as you can see in this slide. 1,650 millimeters for the length, 160 millimeters of diameter, and 3 millimeters of thickness made by, and this component will be made by E-glass epoxy, and all the calculations were made by our team analytically. We adopt a safety factor, as you can see, of 2.12 for the alignment, for the fuselage thickness, and for the alignment rings, we use a material of nylon, and the length of the alignment rings is about 15 millimeters, and it has 140 millimeters of internal diameter and 10 millimeters of thickness. Well, in this part, we had some design requirements, and we need to assemble all the parts about the motor section were the fins, the coupler, and the main bulkhead to sustain the loads and for the motor thrust. And one about the critical points we had this in this section, we need to sustain all the loads from the motor thrust and some another aerodynamical loads and weight. For next slide, please, Augusto. And here we have one simulation that we've made to see if the alignment rings and our decision to use nylon as the main material to be made, and we got a maximum engine working temperature of 240 Celsius degrees, and the limit of the temperature for the fuselage were about 140 degrees. The results shown us that we need to use three nylon alignment rings, and the temperature of contact will be around 100 graus Celsius. And I think that now recovery section teammates can go. Thank you.
Okay, so presenting the recovery. Since the SDR, there have been some changes in the design of the parachute's deployment, as you already saw on the recovery presentation. The current design places each parachute on the sides of the midsection, and the fuselage is always also going to be the E-type fiberglass laminated with epoxy resin. This design requires a fuselage that is thick enough to withstand the pressure of the parachute ejection, as well as all the other typical loads at the fuselage. And as weight is a critical aspect of this design, we also wanted the tubes to be as lightweight as possible. So in order to solve this, we made a pressure vessel analysis on these tubes. We looked for the stress and deformation occurring on each tube, given the pressure needed to deploy each parachute. So the picture shown here illustrates the total deformation on the main parachute tube. And this kind of analysis was made for both the drogue and main tubes that have a length of 300 and 600 millimeters, respectively. And with an overall safety factor of 3.17 for the drogue section and 6.6 for the main section, the tubes were defined with a thickness of 3 millimeters. Now, if you go forward, Flavio will explain a little bit about the midsection.
Hello everyone, my name is Flavio. I'm going to talk more about the midsection. The middle section is where we're going to place the avionics and payload bays, and it's a section that had many requirements that take into consideration. This section needs an internal structure to provide extra relief to the fuselage, for more security to the internal equipment, and also release the base from having structural holes. So the design requirements are the internal structure has to offer protection to the avionics and payload bay, as well as easy integration. So we focus to our design to be simple, objective, lighter, and modular as possible. Thanks to the real team effort, we think and analyze a few designs to reach this final one that consists of 4 M8 thread rods that are fixed to the recovered bulkheads by hexagonal flanged nuts. These rods are made of alloy Icing 1020 and are 720 millimeters long. With this, the payload and avionics base can be easily integrated to the structure, giving it the simplicity and versatility, especially for the payload. The total structure mass is around 1,200 grams. With these technical features, we can conclude that the design attends to all the requirements. For the fuselage of the section, it has the length of 700 millimeters with a 3 millimeters thickness, all that with a safety factor of 4.6. Now I will return the word to Livia.
Okay, so the avionics bay has also changed since the STR. You already saw also the avionics presentation. So it's now unified and inside the midsection, and the bay consists of an open stack structure of 3 aluminum plates where all the avionics components are placed inside the length of 200 millimeters. For this design, we had to take into consideration the weight of the batteries, the height of the antennas, the passage of wires between components and the recovery, and also the precise positioning of the cameras. So because of the batteries, as I said, which are the heaviest components, the inferior plate is defined with a thickness of 5 millimeters, while the other ones are defined with a thickness of 3 millimeters. So the positioning of the cameras was a bit tricky because we have a structure of 4 rods, but we need to place 3 cameras equally spaced at 120 degrees. So to ensure that the cameras are integrated correctly, we propose using hexagonal plates in which the cameras will be fixed on every other vertex. And to place the camera in an angle where we can see the ground, we also designed a camera mount of PLA and a window of a polycarbonate piece covered by fiberglass that extends a little bit outside the fuselage. And in concern to the antennas and wires, as you've seen, the shape of the plates and also some holes provides enough space to arrange all of them inside the bay. That is all.
Okay, so reaching the end of the presentation, here we have a table with flight envelopes of the rocket. So first of all, we have the mass during pre-launch. It should be around 64 and 67 kilograms. The CG position should be around 254 to 259 centimeters. The maximum average airspeed should be around 5 meters per second. A maximum one, and the launch rate velocity should be around 30 to 40 meters per second. If all these conditions are met, from our perspective, from the aerodynamics and structures perspective, we can assure that the rocket will perform a stable and safe flight. So that was our presentation. Thanks a lot. And do you have any questions?
Thank you very much, Augusto. Questions and answers now.
So, thank you, guys. The presentation was brilliant. Congratulations for every piece and every part of your work. So, I have a question, please. Could you put the presentation again?
Yeah, sure.
Thanks.
Just a second. Okay.
Thanks. So I have just a question. If you can go back to the fuselage part of the engine section. Yes, motor section. My first question is, you are saying that the fuselage is made of E-glass epoxy with a length of 1.6 meters with a thickness of 3 millimeters and a mass of 5 kilograms. Is that correct? 5 kilograms for 1.6 meter of 3 millimeter thickness of fuselage for the motor bay?
Yes, according to like the CAD that we've done, we used an approximation because E-glass by itself has a density of about 2.5 kilograms per, I don't remember exactly, but I don't remember the exact name, the exact value, but it's a little bit high when you look at it. It's almost the same as the aluminum. But the thing is, we are not using only E-glass. We also, when we are going to laminate and stuff, we are also using epoxy, and this lowers a little bit the density of the composite material. So we got some. Of course, this is really difficult to measure when you don't have actually your material. But so what we've done, we've got information from other teams that have already worked with the same fiberglass and the same ways we are expecting to use it, and we got from them the density, and then we calculated the mass, and this is the mass that we've got.
Okay, thanks. Just a second question. Normally,
Yes.
Student rockets for a 3-kilometer apogee, for example, they have normally 4 millimeters to 6 millimeters of thickness. So I think trim this way, but we during the test part of our roadmap for launch, we will have to test a lot just to make sure that the safe factor is over 1.5 to 2. Okay, it's just a heads up. It's not something that I'm worrying about, but it's just a reminder. So my second question is about the alignment rings made with nylon. I did not understand a lot about these kind of holes. Are you going to put some a bar inside these holes? I didn't get it.
Actually, these holes are just to decrease the weight of the rings.
Okay, fine. It's because a few years ago I saw something like that, but with bars inside it. So okay, I don't need to worry about it. So I think it's okay for this part. Could you go to the fins, please?
To what? I'm sorry?
For the fins.
Oh, yeah, sure. Of course.
Okay, nice. You are saying that with 3 fins, you are expecting a 1.7 calipers for the rocket. Okay, 1.7 is okay. I highly recommend for something about 2 calipers. Okay. Next slide, please.
Sure.
Next one. Okay, you can go back for the first one.
This one?
Yes,
Okay.
nice. We have some kind of interesting thing here. I think you guys did a great job, okay, with the balsa, the plywood, okay, and with the hexagon design for the supersonic part. I'm worried, but about the aerodynamics effect. Okay, I know that you guys are in the preliminary design review, but with a supersonic regime, we need to worry the transonic regime to the supersonic regime. We need to worry about the aerodynamic effects. For example, you have a balsa, a plywood with a layer of carbon fiber, for example, and I think with for example, the transonic regime and all the effects happening in that zone, we need a complete analysis of the aerodynamic effect. For example, a few years ago, I was watching a video. I will share with you. The video of the rocket is a amateur rocket. The rocket has a onboard cam pointing to the ground, and when the regime reach a transonic to supersonic, we can see the fins doing something like that, like flapping. It's very interesting. So I think this is something that you guys have to analyze for the critical design review, the aerodynamic part, and more. I think something that is very, very, very important is how you guys are going to attach the fins to the body of the fuselage. Because if you guys just put a 3-point of anchor, for example, 3 screws, it's not going to work. We will lost the rocket during the ascent phase. So I think you guys have to do a homework that's going to analyze the aerodynamic effects on the fins, and I highly recommend to verify if 4 fins, a pack of 4 fins may help this possible problem. I don't know if it's a problem. You guys will work on this to say if it is or it's not, but I'm worried about it because the length of your fins from the fuselage to the tip is almost 20 centimeters. It's a lot. It's a lot. So I think you have a very, very is not very, is a big difference of pressure between your tip and your root. So maybe this is going to for example, be something that will affect the LASC effect in the thing. So I think this is going to be something you need to work in the next phase of the design review. But I really liked your design. It's a unique design in Brazil. I'm working with rockets since 2009, and I worked with a lot of people, a lot of teams, and I think these things is the most complex thing that I have seen since 2009. So congratulations, and I think the work is amazing. It's not just a CAD. You guys did a lot of base research and algorithms. You guys studied a lot on this matter, and I'm really happy with everything that you guys done in this presentation. So I have no more questions. I think Gabriel and João, they don't have any other questions. I think you just need to go to the critical design review from now and work on the most important part now. It is the CAD and how you guys are going to build, to produce, to manufacture this amazing rocket that you guys are building here. So congratulations, and we will see you again in the critical design review.
Sure. Thanks a lot for the kind words, Calvin. It means really a lot for us. And just a little comment on the air elasticity thing. Yes, this is something that we are worrying a lot. As you can see as well, the aspect ratio of our thing is kind of big as well. We run a few simulations using aerofin simulation, and this is one of the reasons why we chosen carbon fiber as well, is that for us to make to be sure that the thing structure won't have any damage due to air elasticity effects. But yes, we are totally planning to tackle this this topic during the CDR. Thanks a lot for the advices.
So nice. Do you guys know what is your max Q, the maximum dynamic pressure?
I'm not sure. I think we don't we didn't have time yet to do a full scale CFD analysis. So actually, yeah, we don't have this information yet.
No, it's okay. It's okay. Nice. Congratulations, guys. Nice work. So Vinicius, go on.
Okay, thank you very much. Thank you very much, Augusto and team. It was a very nice presentation. I hope everyone enjoyed a lot. And now let's go for the last part of the meeting. Let's go for the propulsion time. We have Felipe and Igor, PMOs, and the propulsion team. They're going to present us what it takes to take a massive rock like that into 5-kilometer apogee. Now, Felipe, can you hear me?
Yes, I can hear you, Vinicius. Thank you. Good evening, everyone. My name is Felipe, and I am the Vice PMO for the Propulsion subsystem. And we will be presenting the work we have done in the preliminary design review, along with Andres, Anna, and Christopher. So let's start with the internal ballistics. Let's start with the objectives. So the main goal is to power our vehicle to a 5-kilometer apogee with the following vehicle characteristics. So we have a mass without a motor of 29 kilograms, an average drag coefficient of 0.5, and a frontal diameter of 117 millimeters. The best results we got were the ones with a variable core base configuration. And we have used the KNSB propellant, so potassium nitrate and sorbitol, formulation, 65 and 35, 7 grain segments, 114 millimeter outer segment diameter, 200 millimeter segment diameter, and we have 4 grains with 45 millimeters of core diameter, along with 3 grains with 60 millimeters of core diameter. You might be questioning yourselves why we have chosen the variable core configuration, and that's mainly because of to prevent any erosive burning effect on our motor, as it may improve our motor safety. It makes our propellant a lot more predictable, and it might lessen the max acceleration of our vehicle. Here we have some of the results we have got with our simulation. So we have a max pressure of 5.5 megapascals, a max thrust of 8.5 kilonewtons, a propellant mass of 19.76 kilograms, max Clemmung of 367, burn time of 3.81 seconds, thrust time of 3.93 seconds, total impulse of 24.26 kilonewton seconds, and an O-class motor. Also, the specific impulse is 125 seconds. Here we have the main results, the graph we have obtained from our simulation. And on green, we have the chamber pressure. And you can see we have kind of 2 stages of the chamber pressure. We have the main stage, which is when all of the segments are burning at the same time. And we have a smaller, lower chamber pressure section, in which only the 45 millimeter core diameter segment grains are firing. Here you have also a trajectory estimation. So this trajectory was made with the latest updates from the structures and all of the other subsystems. So we have a vehicle mass without the motor of 28.88 kilograms, drag coefficient of 0.5 as said earlier, and frontal diameter of 170 millimeters. And also the motor structure is 17.59 kilograms. With this exact configuration, we have got an apogee of 5,303 meters with a time to apogee of 31 seconds. So it is going to be quite a long flight, relatively speaking. And we might reach a maximum Mach number of 1.15. Maximum acceleration of 14 Gs is also within the expected range. The total flight time may stay within 10 minutes and 14 seconds with all the recovery data we have got. So here we have the velocity plot and the acceleration plot. The velocity is the green curve and the acceleration is the orange curve. So we have a peak acceleration at the motor burnout, and then we have smaller acceleration peaks when the recovery activates. And here we have the same flight data. And now let's pass to the structural design. We have decided to keep a conical nozzle for our structure, mainly because of the manufacturing. We are going to see more details of the manufacturing in the CDR phase, but anticipating some of that, we have kind of mainly decided that the plan A is going to be the conical nozzle. We're working with a 5.5-inch 6061 T6 aluminum casing for our main architecture, a 6061 T6 bulkhead, a safety factor of 4, and 16 fasteners of M8 1.5 screws on each side of the parts. The total length of the motor is going to be almost 1.7 meter, and the total dry mass, as said previously, is going to be 17.59 kilograms. So here we have more information about the casing. The casing is going to be made out of 6061 T6 aluminum. We have already confirmed with our supplier. The outer diameter is 139.7 millimeters or 5.5 inches, and the casing length is going to be 1,588 millimeters. Sorry, as said previously in the structures presentation. So for the fasteners, we have decided to go with a 16 screw count, radial screws, equally spaced. They're going to be M8 screws, so with the threads 8 millimeters of outer diameter, and a thread pitch of 1.25 millimeters because it's the most common and it's generally pretty standard. This yields us a safety factor of around 5 or 6, depending on the if you're calculating for shear or compression or tear. More information about the bulkhead. We have 6061 T6 aluminum also, and the thickness is going to be 10.2 millimeters. This also yields us a safety factor of 4. So for the nozzle, we have a material 304 stainless steel. This is pretty standard also for a nozzle. It is pretty heat resistant. A conical profile, which is also pretty standard, pretty easy to manufacture, which is certainly a plus in this range of diameter. A throat diameter of 36 millimeters, expansion ratio of 8.67, which optimally expands through most of our operation. This was actually optimized for the max thrust. Convergent angle of 45 degrees and divergent angle of 15 degrees. The divergent angle might go down a bit on the CDR, but that is the current one which we got the max apogee of. And now I'm going to pass to Andres. He's going to talk about the thermal analysis of the motor.
So good evening, everyone. My name is Andres. I'll be talking a little bit more about thermal analysis. So as selected on SDR, the material used on thermal protection for this one is EPDM, as you can see on the presentation, okay? So in order to estimate the thermal distribution along the case and also along the bulkhead motor, we developed a new software called Rocket Thermal Analysis, as you can see it in the right-hand side image. So to achieve this task, okay? So after more than 60 simulations, we estimate around 3 millimeters thickness of EPDM to have a good security during the flight. And also for the worst case in which we assume no convective heat transfer, and again, I will repeat this, no convective heat transfer, this will not occur, okay? We estimate the temperatures that you are seeing in the presentation. So for the aluminum, in this case, the limit temperature to operate is around 270 Celsius degrees. So as you see, we will be in the safety zone. And furthermore, this level of temperature will be reached only after the operation of the motor. So Felipe, you can go on, please. So this is the final temperature of the case for a multiple thickness that we run the simulations with RTR. So please go on. This both images is for the temperature distribution of the case and also with for the bulkhead, again made it with RTR. Please go on, Felipe. And this is the temperature at coasting phase. You see that we are in according with the spec when we simulate that experimentally. So thank you all.
Good evening,
yes,
everyone.
Thank you, Andres. Sorry, you can speak now.
Good evening, everyone. I am Correa, and I'm going to present the propellant manufacturing and burn rate. So for the manufacture of the propellant, we'll use the composition of 35% of sorbitol and 65% of potassium nitrate. So that the nitrate be pure, it will be purified through the crystallization process. There is an image of the crystallization process of GTE team illustrating this process. After that, the grams of sorbitol and potassium nitrate will be sieved and homogenized to ensure a better quality. This mixture will be cooked with temperature monitoring, and then it should be placed in the molds of the grams. To analyze the burning rate, we will do two types of tests. The first will be done with ambient pressure, and the second with a motor test, like this shown in the image. This motor will be a scaled-down version of the official 5 km motor, and will have the same target chamber pressure. This test will be used to measure the burn rate as the chamber pressure operating range. These processes will take place before the static test to ensure a greater security.
Yes, great, Adam. And Christopher, you can talk now.
Good evening. I am Christopher Deep, and I will talk about the inhibitor a little. So our main option, it's on the inhibitor. We go in with the fiberglass because it has the best characteristics for what we want, and especially having a great resistance to heat. Fiberglass is a bit boring to work, do the process, and have to do, but because it's well documented, it brings more reliable when using. The next. So we have two alternative options that using PVC tube for for the inhibition, with an internal layer which hasn't to integrate the gram and the inhibitor. It would make it easier to prepare the grams since it already serves has their own mold. But unfortunately, because of the tubes already found, we saw that we would need work on the outside diameter. So we didn't know how the behavior would be like. So we left the aside because we need to do some testing with. So at the moment, we keep the fiberglass.
Yes, thank you, everyone. Now we are open to questions.
Okay, thank you very much. Questions and answer time with you, Calvin.
Thank you so much, Vinicius. Thank you, Felipe and our team. The propulsion part is something that I personally I like a lot. Is my knowledge part when we talk about rockets. We had a meeting before the PDR. It was like a pre-PDR, and I think you guys did a great work. I already said it to you. I just want to make a few mentions here. I'm very, very happy to watch Ana Correa presentations. I think this is something great to have Ana and the GFIG team with us. Congratulations, Ana, for your presentation. I think Christopher and the person that is presenting, sharing the screen, please go back to the PVC alternative option. Okay, guys, I know this is a alternative option, but I think you guys have to go with the fiberglass. So please go and focus on the fiberglass part. If something happens and the fiberglass it's not something that is good to go, we can go for another type of a inhibitor, but I'm not comfortable with PVC as a inhibitor, because the PVC normally you have a lot of work because you have to sand inside the tube to have more adhesion, and something that it's very, I think you guys will have to work a lot. So I don't know if it's a good option for a backup plan, but it's a backup plan, so it's okay. Let's go with the fiberglass. I think this is going to be something very interesting, and I'm very anxious to go to the test site for the first hot fire test as soon as possible. um, Finishing my talk here, I'm very happy and very glad to have you guys work in this project. The propulsion system is very complex, and I think you guys did a great work. There is no consideration of my part in the propulsion system. I think this is going to be the most energetic propulsion system from the Latin America, made by a student group. So you guys are going to make history. It's going to be a record. I think this motor is very, very complex, and you guys did a great work. I have no words. I'm very glad. I just want to say to Felipe Bogart and Igor Novs. I know Igor is not here tonight, but the pressure is a bit high. It's 5.5 megapascal. I'm not I'm not comfortable with this kind of pressure. I prefer to use something between 500 to 600 psi. But I think we are good to go with a 800 psi, and I think this is going to be a huge motor. The sound of this motor will be impressive. I'm very anxious to go to the test site to watch the test. So congratulations, guys. We don't have any kind of word on the propulsion system. So we are done for the preliminary design review with all systems. We have a lot of homework to do, but for the New Year's Eve, you guys are go. You can sleep well tonight. And you guys did amazing work. Congratulations for the dedication, for the time, and for the motivation to do this project. I think in February or March, we will announce something very interesting for this project. Nowadays, this is a little bit secret, but I think you guys will like a lot. So congratulations, Vinicius. From LASC part, that's it. Let me ask my colleagues if they have any other questions or any other word to talk. So you can go, João.
Everything's okay here. You can mute. Yeah, everything's okay here. My part, the avionics part. For me, is everything really okay, and you guys really did a nice job presenting everything here. And you brought us the cards, the circuits, and the information that we needed. We just discussed something about the remove for flight, but as I said, that was not wrong. It's just that people prefer to do it some other way. And thank you for the presentation. Thank you for the time put into this. It was really awesome. Yamato, do you have something to say?
Yes, thank you, João, Calvin, for all structure, propulsion, avionics, recovered. Everything was really great. I think we are on the we are going to have a really good project, as Calvin say, Latin American braking project for LASC 2021. And just one overall recommendation for the next presentations. I think it will be great to have some slides about the overall of the rockets, like some parameters like rocket total length, mass,
maximum velocity, and everything resumed on one or two slides about the overall of the rocket. And I think everything was really great. So thank you very much, Al, and that's it from my side.